In this video, we're going to see how we can solve geometric problems using the roots of complex numbers. So in the previous video, we saw how when we solve problems such as z cubed equals 1, we got the three roots of that equation formed an equilateral triangle. And we saw how when we solved z to the power 4 is equal to minus 2 plus 2i root 3, the roots of that equation formed a square, a regular square. So this lesson is all about how we can use that information to help us to solve geometric problems. So here's the first example we're going to have a look at. We're told that the point P, which has got coordinates root 3, 1, lies at one vertex of an equilateral triangle. The centre of the triangle is at the origin. Find the points of the other vertices on the triangle and then find its area. So I've already started this question off a little bit here. So the fact that I was told that one of the roots was at point P, which is got the coordinates root 3, 1, that's telling me that the first root has real component root 3 and imaginary component 1i. Now, in order for me to find the other vertices of this equilateral triangle, I want to find the other roots of my equation. So I want to work in exponential form. So I want to rewrite this in re to the I theta. Well, I can do a little bit of Pythagoras here. So root 3 squared plus 1 squared is 4. Square root of 4 is 2. So I know that the modulus of this number is 2. I now want its argument. So if I did tan theta is equal to 1 over root 3. So the argument there is pi over 6. So now I've got my first root of the equation, whatever that equation is. I can find the next root by multiplying the previous one by my omega factor, the w factor. The w factor, remember, is e to the 2 pi I over n. And in this case, because it's a triangle, n is 3. So the modulus will stay the same. And then I'll have e to the pi I over 6 times e to the pi I over 3. Adding those arguments together, and we get 5 pi over 6. And then to get the third root, again, we're going to multiply our previous one by e to the 2 pi I over 3. The modulus will stay the same. E to the 5 pi I over 6 times e to the 2 pi I over 3. The 5 pi over 6 plus the 2 pi over 3 gives 9 pi over 6, or 3 pi over 2. Or if you prefer, we could turn the 3 pi over 2, which remember is like that, into the minus pi over 2. So we should do that actually. So we have the three roots of the equation, which are going to represent the three coordinates of the vertices. To plot those, let's turn them into coordinates. So let's turn each of them back into Cartesian form. So here the modulus is 2, we'll have cos, the argument is 5 pi over 6, plus I sine 5 pi over 6, which gives me minus root 3 plus I. So that's my second root, which as a coordinate is going to be minus root 3, 1. And then the third root will have 2 cos minus pi over 2 plus I sine minus pi over 2, which gives minus 2i, which is the coordinate 0, minus 2. So let's plot those other 2 points onto my Argand diagram. So the coordinate minus root 3, 1, is there. That's the roots corresponding to Z2. And then the roots corresponding to the third root there is 0, minus 2, which is going to be there. And so our triangle looks like this. We need to find the area of that triangle. Well, in this case, it's quite easy because we can just work out the area. We can just do base times perpendicular height divided by 2. The base is the difference between those x coordinates, so that's going to be 2 root 3. The height is going to be the difference between these y coordinates, so it's going to be 3. So the area of that triangle, half base times height, and we get 3 root 3. That worked out quite nicely because we had, quite clearly, we had a perpendicular height and base. It was quite clear that this and this were perpendicular and can be found quite easily. Do remember though, we can do other methods here because we do know as well that each of these angles is 2 pi over 3. So if I know that this is 2 pi, if I know this angle here is 2 pi over 3, and we know that this here is 2 and this here is 2, then we can start to do half AB sine C to work out the area of this triangle here, and then times it by 3 to get the area of the whole triangle. So there are other ways of working out the area of the triangle if it's not quite so simple. For example, in this question here, we had the roots of the equation z to the power 6 is equal to 7 plus 24i. And I've worked out the first couple of the roots of that equation as being the 6th root of 25 times e to the minus 0.2145i. And I did the second root there, and then we could work out the f1s using the method from the last video if we need to. And I could turn each of those into Cartesian form and plot all of those as coordinates, and then try and work out the area of the hexagon from there. Alternatively, I do know that the angle here is going to be 2 pi over 6, because we know the whole angle there is 2 pi, and there are 6 different angles here. So I know this angle here is 2 pi over 6, or pi over 3 if you prefer. I know this is the modulus of one of the roots, and that's going to be the same here. And so I could start to work out the area of one of those triangles using the formula half times A times B times sine of the angle in between. That would give me the area of one of these triangles, and then could times it by 6 because there's 6 of them obviously. So there are other ways of working out the area of these shapes, remembering your sine rule and trigonometry rules. The key thing really is remembering the angle in between each of the roots, and the modulus is the distance from the origin.